Hello friends, today I'll have a look on CPU scheduling. These are the various topics which are going to be covered. The basic concept, scheduling criteria, algorithms, thread scheduling and multiprocessor scheduling. These are the related objectives of this particular chapter. The slides explains about the basic concepts of why scheduling is required. As we know that every program to be executed has to be loaded onto the main memory. It should make use of the resources like file, registers, I/O devices. So in between it undergoes CPU cycle and I/O bus cycle. So every process execution is going to consist of a cycle of CPU execution, I/O cycle and wait time also. So we need to take care of maximum CPU utilization by means of multi-programming. So usually every CPU burst is followed by I/O burst. We are mainly considering CPU burst distribution in this particular chapter. So as we have already seen the different schedulers of CPU like short-term scheduler, mid-term scheduler and long-term scheduler. The main goal of selecting the processes from the ready queue and allocating them to CPU is a major task of short-term scheduler. So this allocating of processes to CPU is framed by short-term scheduler. It can order the queue by using various ways. It can take the decisions based on various criteria, that what we call as a scheduling algorithms. So when it does such decisions is when a process is running to switching from running to waiting state, or from running to ready state, or from waiting to ready, or when a particular process has terminated and no work to do is left for that particular process. So here as 4 conditions are described when it is preemptive and non-preemptive that we can observe. When a process is willingly relieving a CPU, then we can call it as a non-preemptive. No force is done on the process by the OS. Whereas in preemptive, the process is forcibly made to relieve the CPU and assign it to another process. So all other schedulings like as it is illustrated here, scheduling of CPU under the condition 1 and 4, that is when it is switching from running to waiting on its own, like say an ongoing process wants to make I/O operation, so it has to leave the CPU and do I/O operation. Or else when it is terminating, when it has completed task, so then it has to do nothing with the CPU. So in these two cases it is relieving the CPU on its own. So these two conditions are leading to a preemptive scheduling. Whereas the other, that is when it is running to ready state, that is OS is making it to move out of the memory or preempting it to another process, and it is waiting under ready queue to acquire the control of CPU. So these two situations are all preemptive. So here we are considering accessing of shared data and considering preemption in kernel mode, and it can consider interrupts occur during the crucial OS activities. So these all are preemptive cases. So we'll consider about dispatcher module of the OS, which gives the control of the CPU to the process selected by the short-term scheduler. It involves context switching. We have already studied context switching. It's an overhead or switching process between one process to another process. Switching from kernel to user mode, going to the proper location in the user program and restart the program. These all are the activities carried out by a dispatcher module. So we are going to look into another term here, that is dispatch latency, which is nothing but amount of time taken for the dispatcher to stop the one process and start another running. So again there is a overhead when it wants to switch from one process to another process, that we call as a context switching, and the time taken for that switching is considered as a dispatch latency again. That is the amount of time taken for dispatcher module to stop one process and start another process into running state. So these are the scheduling criteria based on which the algorithms are working. One is CPU utilization, making the CPU as much busy as possible. Throughput is another term, that is the number of processes that can complete their execution per unit time. Turnaround time, amount of time to execute a whole process. It includes the execution time as well as waiting time, the notice waiting time, amount of time a process has been waiting in the ready queue to gain access of the CPU. So the sum of these two, that is waiting time and execution, is going to give us turnaround time. Then we have one more term, that is response time. It is the amount of time taken by the process when a request was submitted until the first response is produced, not to get the complete output. Here I hope you are able to distinguish the term turnaround time and response time. Turnaround time is total amount of time taken to get the whole output, whereas response time is amount of time taken to get the first response from the process. So response time has got more importance, particularly in time sharing environment like websites and all. So scheduling algorithms are optimized based on following criteria. That is, we expect that every scheduling algorithm should have a maximum CPU utilization and maximum throughput. It should execute more number of programs in a particular time and should utilize CPU as much as possible, making the CPU as busy as possible, but it should have the times consumption very less, like minimum turnaround time, minimum waiting time, and minimum response time. So this is I will go for the scheduling algorithms now. First we'll have a look on first come first serve scheduling algorithm, on which we have already seen the problems in the class. Also I have shared a video on this for your revision purpose. So here is a illustration of one particular problem. For the details you can observe the video. Yeah. Another problem is taken where we can have a summary of this compared to this. In this, the same processes with the burst time 2433, but arrival is, if the arrival order is exchanged as P2, P3, P1, then the average waiting time is reduced. It is better than the previous case, even though the burst time is same. The convoy effect you can observe at the end, that shorter process behind longer process are leading to a reduced waiting time. So what does that mean is, if a longer process is waiting for a longer time, then it obviously leads to more waiting time and in turn more turnaround time. So the solution for this is shortage of first, that is SJF scheduling. So here as for the drawback of the previous, that is shortest processes are kept at the behind, then it is giving a good performance. So taking into consideration of this, SJF was developed where each process is associated with its next CPU burst. Based on the length of the CPU burst time, the CPU is allocated. So SJF becomes optimal compared to FCFS, gives a minimum average waiting time for a given set of processes. But the disadvantage of this is the difficulty to know the length of the next CPU first. One solution is we can ask the user to give this information in advance. So this is the example how SJF works. Again, you need to refer the video on SJF for this. Yeah. So this is talking about how to estimate the future burst time of a CPU, how to predict the next CPU burst. It can be done by using the length of the previous CPU burst using an exponential average. So this is the formula here. Usually by default alpha is set to 1.5, that is half, preemptive version of this is called as, this algorithm is called as SRTF, that is shortest remaining time first.